Hello, and welcome to Exploring Axon, a podcast where we discuss Axon and its ecosystem. I am your host and Axonic developer advocate, Sarah Torrey. Today I will be talking with Milan Savic about clustering in Axon Server, and he will also explain how the Raft Protocol works. I hope you enjoyed this talk, and let's have a listen. Hi, Milan. How are you?
Hi, Sarah. I'm great. And you?
I'm doing great. Thanks again for meeting with me again to talk about Axon Server. So this is this is actually my favorite part because as in my music graduate school days, we would talk about like analyzing a piece of music. Now we're starting to analyze Axon Server, which is the stuff of fun, I would imagine. So let's dive right into it. So last time we talked about Axon Server in general, and you explained what the difference between Axon Server Standard Edition and Enterprise Edition would be. So I don't think we need to go through that again. You brought some really awesome points and differences between the two, which was really cool. So let's go right into Axon Server Enterprise Edition, because that's where the fun begins. So let's talk about just briefly what we have in Axon Server Enterprise Edition, and let's jump right into Axon Server Nodes.
All right. When you mentioned to talk about Axon Server, I felt like a deja vu. We already did this session. I mean, come
on. Surprise! We're doing another session. No, I'm just kidding.
Yeah, but I'm glad that we are going to talk about clustering because that's the part that I like the most about Axon Server, how it works. And I'm really passionate about those features. Let's talk about Axon Server nodes. There are several roles of those nodes. So let's talk. Let's firstly focus on primary nodes. They're the most. They're the easiest to understand.
Yeah, of course. And then, of course, if you can kind of touch on the rest of them too, like the message only, active backup, and passive backup, whenever during the session you see fit, that would be great. Yeah. So, but let's focus on primary for now. Go for it.
So primary nodes can store data, and they store data. What they store is basically your events, your event transactions, and they also are responsible for routing messages across the cluster.
Okay.
Yeah, what we opted for implementing a cluster is a protocol called Raft. Why we chose that one? Because it solves the problem of distributed consensus. The problem of distributed consensus is actually when you have several participants in distributed system and they all have to agree on the one specific value. For those issues, you use consensus protocols.
So can you briefly tell me what is a consensus? So I know it's a fundamental problem in the fault tolerant systems, and it involves multiple servers agreeing on values. But can you explain that a little bit?
Yeah, basically that gives you availability on the data. It improves your fault tolerance. If you have a node, let's say a system of 3 nodes, if one of those fail, then you want to have that data available for clients to use, right? And that's why the data on all nodes in your system have to be the same. If it is not the same, then you cannot guarantee, okay, this is not what was written, it is something else, and that's what you should not do in distributed systems. Right? You should always have the same data. When you say that something is persisted durably, whenever you read it, it is the same value.
Right,
That is what a consensus solves.
Okay, so going back to Raft, as you were mentioning, let's talk about. You mentioned 3 nodes. Do the number of nodes, do they always have to be odd numbers, or does it matter?
It is better. Let me explain you why. Because in the protocol, basically, whenever the majority of nodes is up, then your cluster is available. Then you can serve your clients, right? In a cluster of 3 nodes, as long as 2 nodes are alive, that's the majority, your cluster is available. In cluster of four nodes, then now you need to have 3 nodes available. But that's also the
Right.
same for the cluster of 5. So it is better to have odd number. It doesn't hurt you to have even number, but it is better in terms of availability of nodes to have
Yeah.
odd number of nodes in your cluster.
Yeah, and really briefly, I think in Axon Server I think only offer odd number of nodes, right? We only offer like either 3 or 5. Is that correct? Or no?
Not entirely. We recommend that. Of course, you
Ah,
can
okay.
buy, for example, 4 nodes. Let me tell you why. Because then you can. Okay, let me rewind a little bit. In Axon Server, there is a notion of replication groups, and that's
Okay.
basically one instance of your Raft protocol in the system. When you have those replication groups, you can distribute them on different nodes. Usually, you can distribute them on 3 or 5, but for example, if you have 4 nodes, then you can say, okay, first 3 nodes are part of this replication groups, but then second 3 nodes are part of different replication group. So this is a nice thing to have one additional node, so not to have everything on those 3 nodes, for example.
I see. So let's rewind a little bit on my end. And I sort of jumped you ahead. So let's go back to Raft Protocol. Can you explain why do we use Raft and what is Raft exactly? I know you briefly talked about the main points of Raft Protocol, but let's go back and talk about that and also the election process and everything.
All right. So before Raft, there was one protocol that was, and it still is here. It is present in the industry. It's called Paxos. However, people usually struggle to implement that one because it
Yeah.
is really theoretical, and there are a lot of gaps between the actual implementation and the theory. And in those gaps is the devil, right? Because there
Yeah.
you can have some things misunderstood, or just you don't know how to implement them.
Yeah.
And in those gaps usually are bugs. So Raft was introduced to simplify consensus protocols, right? The
Right.
way it is implemented. So that was its primary focus. It is really odd to have that as a primary focus for a consensus protocol, but that was its main focus because people were struggling with previous protocols. It decomposes consensus problem into 2 main parts. There are some other parts that probably will not cover today, but 2 main parts are leader election and log replication.
Okay.
Let's talk a little bit about those two, how they work, if that's okay with you.
Yeah, absolutely. Yes, that was my next question, leader election.
Yes.
Yes.
So when you want to append data to the cluster, you have to go to the leader of that cluster. Okay,
Okay.
this is the data that needs to be appended. Then this leader replicate that log. But how we are going to get that leader? We are going to use election process. What that
Okay.
means? That means that from time to time we are sending certain messages from one leader to other nodes. Other nodes are
Right.
called follower. There is a third type of node, but for now we have leaders and followers. We
Yeah.
send heartbeats from time to time. Okay, I'm alive, I'm the
Okay.
leader. If I'm a follower and I do not hear within a certain time period that is called election timeout, I don't hear from an active leader, then I'm going to timeout and I'm going to candidate myself to be a new leader of that term. What is a term? Basically, it is a portion of time. In one given term, you can have only one leader of the cluster. That's a strong guarantee
I see.
by Raft. That leader, when it is elected, it is available for replicating data.
Okay.
Those elections are not necessarily not good things to have, because during elections your cluster is unavailable. It cannot replicate data, right? So we
Right.
want to decrease the time needed for those elections, and we want to decrease the number of elections in general. All right.
I see.
Now, when we have our leader,
So then when we have the yeah, sorry. So when we have the elections and the cluster isn't available. So when, for instance, when we have an election timeout, can you explain a little bit about that? What is that? What does that do?
Well, basically, that's the time where one of our follower or more of those
Hmm.
followers didn't hear from the leader, and then they
Ah.
would say, okay, maybe I can be the next leader because we don't have a
Mm-hmm.
current leader. I want to candidate
Yep.
myself. That's the third role in a Raft protocol. That's a candidate role, and then I candidate
Hmm.
myself to become the leader for the next term.
Can you have two leaders, for instance?
No, that's one of the safeties of the protocol. You can have only one
Hmm.
leader per term.
Hmm.
And what I'm going to do when I become a candidate, I'm going to ask all other nodes in the cluster, okay, please vote for me. If I
Okay.
receive majority of votes, for example, in
Hmm.
cluster 3 it is 2, in cluster 5 it is 3, including
Hmm.
myself, of course.
Hmm.
I always vote for myself because I'm the best.
Yeah.
Yeah.
Of course.
And if I receive the majority of votes, then I proclaim myself leader. Of course, there are certain safety rules that have to be applied. I
Hmm.
cannot be a leader if I don't have the most recent log entries in my log, so I send that
Hmm.
information, things like that. So there are certain safeties in order to prevent to
Hmm.
elect any node as a leader. So the leader is always
Hmm.
chosen to be the most appropriate one.
So you mentioned that if one of the nodes or the leader sends the messages to the followers, right? And if the follower does not receive the heartbeat from the leader, and that leader is basically put out, and another candidate is chosen or elected by a node itself, if that leader comes back, so if that node comes back up, would that node automatically becomes another follower, or how does that process go exactly?
There are things called, let me just remember, when this leader is not does not receive responses from followers, then it steps down. So it's
Hmm.
called a stepping
Ah,
down. Yeah. So it
I
will
see.
proclaim itself as a follower. However,
Hmm.
it can think that it is still a leader. Maybe there is a network partition, there is small amount of time where it thinks it is a leader. Then it can
Hmm.
send messages to the other nodes. But other nodes will know,
Don't
okay,
respond back.
they will respond telling, okay, there is a new leader. We have a new term.
Ah, okay.
So the term
Hmm.
increased. You're not your leader for previous term, not
Hmm. Yeah.
the current term. And that leader will step down. Okay, I'm not the follower.
Hmm. Hmm. Hmm.
Yeah.
Very nice. And so you mentioned a bit about so the election. So after the election is done, and the leader then can serve the client, right?
Yeah.
And the leader can append log entries and append entries to the RPC. Can you explain a little bit about that?
Yes. All rights go through that leader. Uh,
Mm-hmm.
so leader is going to receive an entry. Usually in Axon
Mm-hmm.
Server, that is in 90% of cases, it is event transaction, can contain one or
Okay.
several events. Then
Mm-hmm.
this transaction is sent to all nodes in the cluster, to all
Okay.
followers in the cluster.
Mm-hmm. Mm-hmm.
Then, when the majority of followers confirm that this is a valid thing to persist in their event stores, then
Mm-hmm.
the leader will proclaim that this event transaction is committed. This is a
Right.
really important point in the protocol. When we say that something is committed, then we guarantee
Mm-hmm.
that this event transaction is going to be available for clients to read the same transaction, so it is not going to be altered
Mm-hmm.
whenever majority of nodes is up. So whenever we have a cluster available, that information
Mm-hmm.
is available for
Mm-hmm.
clients to read.
I see. Now, how about logs? So, when an entry is committed, the information is going to be present in all logs, and it will not be deleted. Is that only for the leader or followers as well?
For followers as well, right? So all those nodes have their own logs.
Mm-hmm.
When there is a new event transaction, it's going to be persisted in the event log. Oh, sorry, in
Mm-hmm.
the in the Raft log. It's going to be
That's
persisted in the
okay.
Raft log, yeah. And
Mm-hmm.
when we do that replication, it's going to be persisted to all nodes at the same position. So if two nodes have an item that is indexed with the same log index in the same
Okay.
term, it has to be the same value, right?
Okay.
That is also a
So do
strong
we?
guarantee by
Yeah.
default. Yeah.
Do we have so when you had a wonderful talk on actually Raft Protocol and Axon Server nodes, and you were mentioning something about the append entries can be used as heartbeat to prevent unnecessary elections and unnecessary
Yes.
unavailability of clusters.
Yes.
Could you talk to me a little bit more about that?
Yes. Yes. Definitely, there is no a specific heartbeat message
Mm-hmm.
because it would be, let's say, a waste of valuable message, because then it would become a little bit more complex protocol, and they really want
Mm-hmm.
to be really easy to understand.
Yeah.
So we use append entries with no data
Mm-hmm.
to represent that heartbeat. So append entries is sent regularly. If there is some information to be replicated, some events to be replicated, then we add
Mm-hmm.
them as a data to that append entries.
I see.
And that's actually how we achieve heartbeats. There is one thing that I want to touch upon that you mentioned, and that's that log entries are always persistent and always available. That's not
Mm-hmm.
entirely true
Mm-hmm.
because when we append log items to the to the Raft log,
Yes.
then when they are committed, it is safe to apply them. What we do, we basically store those events in our event store.
Mm-hmm. Mm-hmm.
But now those log entries are basically useless to us because they are applied. We don't have
I see.
any use of them. So what we're
Mm-hmm.
going to do is we're just going to compact that log. For example, in Axon Server,
Okay.
for each hour, we are going to check those log entries, all log
Mm-hmm.
entries that are older than, let's say, 1 hour. That's configurable. We're
Mm-hmm.
going just to drop them. If they're applied, we're going to drop them because probably we are not going to use them.
I see.
Yeah.
So, okay, fantastic, and that's done through all of the nodes. It doesn't have to
Yeah.
be leader, follower. Okay,
Exactly.
yeah, that's
Exactly.
yeah. So in Axon Server, in our last episode, we touched on GRPC,
Mhm.
and you mentioned briefly that the Axon Server uses GRPC within the clusters. Can we talk about that a little bit?
Yes. So all the communication between the nodes in a cluster is done
Mm-hmm.
via gRPC. Again, I don't want to repeat myself what I said in the previous session. There are a lot of benefits using gRPC because it's built on
Mm-hmm.
top of HTTP2 protocol.
Mm-hmm.
Um, and it gives us all those nice things such as having several streams over one TCP connection, and then we can use all those goodies, let's say, in internal cluster
Mm-hmm.
communication. Yeah.
Yeah, fantastic. You did talk a little bit about Axon Server Event Store, and when these events are sent to the nodes, right?
Mhm,
They're first sent to the leader,
mhm,
and then the leader then distributes this event within the followers.
mhm.
And what happens after that?
After that,
So they're all going to be stored in just as the leader stores it, the followers store it. We did talk a little bit about it, but I want to go a little bit deeper.
yeah, a little bit deeper is the following thing. Basically, you receive confirmation by the majority of nodes that say, okay,
Mm-hmm.
this is okay to be persisted. Then we
Okay.
say, okay, this entry is committed, and that basically means that we have a commit index that
Mm-hmm.
corresponds to that log entry.
Mm-hmm.
With the next append entry message that we send to other nodes, we are going to say, okay, commit index is this one. That means that
Okay.
other nodes can acknowledge that entry to be committed, and
Mm-hmm.
there is a separate process that applies those log entries to the event store, and it will say, okay, let's read all the events from the last commit index to the new commit index, and let's
Mm-hmm.
persist them to the event store. And that's actually what happens there.
I see. Yeah, very good. So let's go back a little bit and touch on some of the things that we talked about during our last episode, which was handling messages in Axon Server that come from, say, Axon Framework or maybe another type of application. But let's focus really on Axon Framework and Axon Server because that's the easiest thing to talk about. So we did mention how the events are handled amongst the nodes. And you also briefly touched on queries and commands last time. So can you talk to me a little bit more about those?
Yeah. Basically, Raft Protocol does not play a significant role here because we use it only to store events. Right? It is to
Sure.
persist data.
Yeah.
When we have other nodes basically subscribing to the cluster, they will send their information about messages that they can handle. And then when you send a message to the Axon server, based on the information of those available handlers, it will know to which specific Axon framework application to route that message.
I see.
Based on the type of message, it knows the routing patterns, uh, and it will know to which node exactly to distribute that message. Yeah. In certain cases, for example, when you're distributing a scatter gather query, you can distribute to several nodes. But and also for events, right? If you have more
Yeah.
event handlers for the same event type in different applications, that message is going to be sent in a pub sub manner to all other nodes.
I see. I see. Very good. So we sort of drifted off the the Raft protocol. Let's come back to it for just a moment. So we handled the election, and there was another point that you mentioned earlier that we used the Raft protocol for.
That was for the next section was append entries, and that's what we talked about when we
We talked about that. Yes, perfect.
distribute messages. Yeah.
Perfect. Thank you. Yeah, I just wanted to make sure I covered everything. So earlier, we talked about different types of nodes that we have. So we mainly talked about the primary and primary node. Can we also talk about message only and also about backup nodes?
Yes, definitely. So message only nodes are used only to distribute messages. Basically, they do not store data. They
Okay.
do not store events. That's why they are, let's say, lightweight. They don't have a large event store. For example, when you want to migrate your data or when you want to move your Axon server nodes, moving messaging only nodes is much easier in
Right.
that sense. And it is they're responsible only for distributing messages.
Yeah.
Backup nodes, there are two types of backup nodes. Of course, they are backing up the event store.
Yes.
The first one, let's talk about passive backup because it is a little bit easier to understand.
Yeah.
Passive backup are part of the cluster, so they are part of the Raft group.
Okay.
They are listening to transactions and they are persisting those transactions to themselves. Of course, they do not participate in acknowledging the transactions, so you do not expect a passive backup node to tell you, okay, it is okay to commit, because you do not
I
care. It
see.
is a passive. It just tries to read those events at the best intention it can.
Yeah.
And it cannot be elected as a leader of the cluster. And that's a passive
Okay.
backup, right? It
Okay.
is really useful in certain scenarios when you just want to have data available if you have a disaster and you want to recover your data.
Okay.
And you don't want to slow down your replication process. You don't want to slow
Sure.
down replication of events. The other type of backup nodes is active backup. Similarly to passive backup, it tracks all the events, it persists those events. However, this type of node also is involved in acknowledging transactions.
I
When you
see.
want to commit an event transaction, you need to have active backup confirming it. Of course, if you have only one active backup and you say that you need, there are no majorities here. It is configurable how many active backups you want to confirm the
Right.
transaction. The problem that can occur here, it is a misconfiguration of the cluster, and you can have one active backup, and you can configure it that you have that active backup needs to confirm the transaction. Then when that backup is down, in that case, your cluster is unavailable because you cannot commit any more entries. It is
I see.
definitely much safer to have at least two backups and one to commit, or to acknowledge the commit. That's the main
So
difference.
two active backups and then one passive backup
No,
is what you were mentioning, or just two backups, just generally?
two active backups, but only
I
one
see.
participates in committing a transaction.
I see. Gotcha, gotcha, gotcha.
It doesn't matter which one. It is a configurable thing. You can say that you need only one confirmation from an active backup. Doesn't matter which one.
Yeah,
And
right.
also, active backups cannot be elected as a leader of cluster. That's also the
Yeah,
difference.
that makes sense. That
Yeah.
makes sense. Fantastic. So we covered Raft Protocol and different types of nodes and message handling. Anything that I missed?
Yeah, we also talked about availability. There are certain
Yes.
patterns that you might want to use when deploying your cluster, Axon Server cluster. Basically, uh, when you're dealing with data centers and availability zones, you don't want to put all your nodes in the same zone. If that zone is down, then you cannot serve your client because everything is down. So
I see.
you want to
Yeah.
have at least two zones. Of course, that's also not a great scenario because when you have
Yeah.
two zones, one will have the majority of nodes. If
I
that
see.
zone is down, then you have a problem. The best scenario is to have at least three zones. Then
Yes.
one of those three can go down, then the other two can form a majority and your cluster can function. And that's really important to know when you're configuring your cluster deployments.
One thing that I forgot to ask you, for instance, when a leader is down and another follower node elects itself and becomes a candidate, um, how does that work? How does that node become a candidate? Does it have anything to do with the speed of the heartbeat or
Yes.
how quickly the information passed on?
Yes, definitely. We see in certain deployments, in certain environments, that, for example, if you have really slow machines or if you have really high throughput on the system and your machine just cannot support that, then heartbeat messages are a little bit delayed.
Yeah.
And when election timeout passes on a certain follower, then that one can say, okay, I didn't hear from the leader in a certain period of time. I'm going to promote myself to the candidate, and I will ask other nodes. I'm going to ask all the nodes in the cluster to vote for me.
Right.
That's basically what happens. And those are two time periods that you can configure based on your environment. It is not that trivial to do. We have some recommendations, uh,
Right.
and basically based on those two time periods, you can see when your elections are going to happen.
So I think my final question: can we have more than one candidate,
Yes.
and what happens then?
The one that gets the majority of nodes win. Of course, if you have two nodes that have the same amount of vote, then you have a new election. So it goes very
Ah, okay.
heavily. Of course, the probability, there's a theoretical probability that this can happen two or three times in a row, four times, or basically can happen indefinitely, but practical
Yeah.
um, probability is really low because all those
Okay.
timeouts that we talked about are randomized, right? If your
Ah,
random generator is good, and probably it is, your chances of happening two elections in a row is really slim.
okay. Good, good, good. And that's, I think, one of the things that makes Raft Protocol really kind of ideal for our use case, at least,
Yeah.
because it's reliable and it's simplified, which is something that I like about it. Yeah, and it was interesting because I had a conversation about I didn't know about Raft Protocol until a few months ago, and our colleague Sarah Pellegrini was explaining the Raft Protocol to me gosh, I can't talk today. And she showed me this small short animation, and it was just so easy to understand and so wonderful. Because of course, this is sort of when we talk about software programming, this is sort of like the back end of the back end, right? This is really getting nitty gritty into the server stuff, but it made it so much easier to understand, so much more palatable actually to look at, and got me excited about server, which wasn't something I thought I would ever say, but yeah, it was really cool. So thank you so much for uh, sort of going more into detail about what it is and how the election process happens, and why that is important within Axon Server. So I really appreciate it. As always, any final points you'd like to add at the end?
Well, there are a lot of points that should be added to
Of
have
course,
to have the clear picture how everything works, but I believe that it's going to be too confusing if you go into too much details.
too much detail. Yeah, and of course, every case point is a little bit different. So
Yeah,
it's great. Well, thank you so much again for joining me, Milan. I really, really enjoyed talking to you this past couple of times, so I really appreciate it.
yeah.
Thank you.
Thank you for having me. It was a pleasure.
Oh, pleasure is all mine. Have a great day.
Yeah, you too.
Talk to you later. Bye.
Bye bye.
Thank you so much for listening. I hope you enjoyed our talk. Please join me next time as I delve into other topics such as Saga, event modeling, and more. Until then, have a great day and happy coding.